Good afternoon, friends, and welcome to another session of the Physics Class 12. As you can see, today we are going to discuss a very important topic of optics, which is Huygens principle. Okay, so this is the topic for today, Huygens principle from optics, and we will be dealing with Huygens principle along with interference of the light. So this is Parijat sir classes going on, and you can comment and WhatsApp me in this number. This is my personal mobile number. You can contact me here for any personal guidance or for any suggestions or any of the things you are facing any problem. You can contact me directly in this. So I would request you to please go through all my videos and so that you can get a complete idea of the theory and the numericals. So please like, share and subscribe so that you can get updation of any new videos which are uploaded, and you can go through the numericals and the theories. You don't have to prepare any extra thing on your own. So you can directly go through the theories and make the notes out of them for your board examination. So let's get started with another topic of physics, which is Huygens principle, a part of optics. So let's see what is there. First we will be studying what is a wave front. First we will study what is a wave front. So friends, you can see here, it is a continuous locus of all particles of medium which are vibrating in the same phase. Same phase means, see, this particle is vibrating and sending waves like this. So as you can see that this particle which is vibrating and sending waves, so each and every progression of the wave is creating a surface which is called a wave front, and they are all in phase, means none of them is longer or none of them is shorter. None of them is longer and none of them is shorter. So that is called same phase. They should all be in the same phase and vibrating in the medium, and which will produce surfaces which move out from the vibrating particle. So this type of vibrations can produce how many types of waves? One is a plane wave front. As you can see, plane wave front means the waves will be moving like this. The waves will progress like this. So since the waves look like planes, so we call it as a plane wave front. Second, see, this is a plane wave front which is moving forward. Second is a diverging spherical wave front. Diverging spherical wave front. So please note here the terms also. This is a diverging spherical wave front. So see, it is coming out in the shapes of spheres, and that is possible if a single particle is vibrating. Next is a converging spherical wave front. It is possible if the wave fronts are converging to a point. Converging spherical wave front. Okay, so here as you can see, the rays are always normal to the wave front. This is a ray which is perpendicular to the wave front, which is perpendicular to the wave front. This is perpendicular to the wave front. This is a ray which is perpendicular to the wave front. Ray perpendicular to the wave front, as you can see. So these rays are perpendicular to each and every wave front, perpendicular to the wave front. So whatever wave fronts you take, any type, the wave will always be normal to the wave front. Next, let's see. So we are now going to study what is Huygens principle. What is Huygens principle? Very important topic. What is Huygens principle? Okay, every point on the given wave front called the primary wave front. So what is a primary wave front? The first wave front is called the primary wave front. This is the first, this is the primary wave front. This is the primary wave front, and after this we get the secondary wave front. So this is the primary wave front, this is the secondary wave front. Similarly, this is the primary wave front, and this is the secondary wave front. So HYGENS principle tells that every point on the given wave front, that means from on the primary wave front, if you take any point, acts as a fresh source of new disturbance called secondary wave front, which travel in all directions with the velocity of light. That means the primary wave front from every point will give rise to secondary wave front. Okay, so the primary wave front, this is the primary wave front which will give rise to the secondary wave front. Every point in the primary wave front will give rise to the secondary wave front. Okay, and that wave front will always travel in the direction of the primary wave front with the speed of light, with the speed of light. This was the first principle of HYGENS. Second, a surface touching these secondary wavelets tangentially in the forward direction at any instant gives the new wave at that instant. That means if you draw the tangents at any point, if you draw tangents at any secondary wavelet, if you draw tangents at any secondary wavelet, it will tell you which direction will the wave travel, which direction will the wave travel. That is what is called. So that is the secondary wavefront. Clear? So as you can see here, this is a source which is which is creating vibrations, though this is the primary wavefront. Okay, and they give rise to the secondary wavefront which progress in the direction of the wave. Similarly, this is the primary wavefront which give rise to the secondary wavefront. Okay, and they travel in the direction of the wave. So that is what HYGENS was telling. Next is reflection on the basis of wave theory. That means we will be now studying that this wave theory obeys the laws of reflection. So let's see. So let us take a plane wavefront. Let us take a plane wavefront which will strike a mirror M1, M2. This is a plane mirror which will, here a plane wavefront will strike. So till here, you see, till AB, all the particles of the wave, they travel in the same time. Now when A hits the mirror, B still has not hit the mirror, right? So when A has hit the mirror, it started to suffer reflection and reach till B dash. When A has reached B dash, B will reach A dash. B will cover the distance A dash. When A has reached B dash after reflection, the B will cover the distance B A dash till the mirror. Okay, so we are taking 3 incident rays, 1, 2, 3, and it is falling perpendicularly. So that means from that the secondary wavelets from B strike M1, M2 at A dash. That means the time in which A will reach B dash, B will reach A dash, right? The secondary wavelet. So let that time be t seconds. So what is the time traveled by B to A dash? It is C into t. It is C into t. Time to travel from B to A dash is how much? C into t. That is the distance B A dash. That is the distance B A dash. Correct? Now the reflected rays of the one is traveling from, as you can see, the reflected rays from one will travel in the direction A B dash. From 2 it will travel in the direction, this is the 2 dash, the reflected ray of 2. The reflected ray of 3 will travel in the direction of 3 dash. So let the angle at which ray 1 strike be I. Let the angle at which ray 1 strike be I. Okay. So now as you can see from here in the diagram, okay, as you can see in the diagram, what is happening? See, this is the angle I. If this is I, this is also the angle I, because this is 90 degree. So this is also acting as angle I, correct? And this is the reflected ray making an angle R. This is the reflected ray making an angle R, correct? So this also will be angle R. This also will be angle R. Okay, so now we can say that angle of incidence I told you, angle of reflection I told you. Now please watch the two triangles A dash B. Please watch, where is A dash B? This is A dash B, A dash B and A B dash A. They are similar triangles. They are similar triangles. So they act as similar triangles. These two triangles act as similar triangles. Okay. And the distance from B to A dash and A to B dash. Please watch here. B to A dash and A to B dash, this distance B to A dash and A to B dash should be same, because it is in the same medium. It is in the same medium. Clear? Should both be C into T. Okay. Now angle B and angle B dash. Please watch the figure. Angle B, this is the angle B, and angle B dash is 90 degree. So in the two triangles there is a 90 90 and a common side. A dash is the common side, and B A dash is equal to A B dash. B A dash is equal to A B dash. So see, the two triangles are congruent, so I can tell angle I is equal to angle R. So I can easily tell angle I is equal to angle R. Okay, the two triangles are similar as well as they are congruent. So if they are congruent, the triangles are congruent, then this angle should be equal to this angle. That means angle I is equal to angle R, which is the first law of reflection. So this is only called as the first law of reflection. Okay, so similarly, the incident wavefront AB and the reflecting surface M1 M2 and the reflected wavefront A dash B dash all are perpendicular to the plane of the paper. So please watch here. This is the incident wavefront AB. A dash B dash is the reflected wavefront, and the mirror all lie in the same plane. All lie in the same plane. So that was supposed to be the second law of the reflection, which is also being followed here. That means the laws of reflection are being followed according to the wave nature. Okay, so here we are able to prove that angle I is equal to angle R, and that is the point where we can tell that yes, laws of reflections are obeyed when rays are falling on a mirror. Similarly, refraction. Now we have to prove that yes, refraction is also possible. We have to prove now that on the wave theory, refraction of light is also possible. So let us see the figure. So this is a surface. XY is a surface whose refractive index is mu. So this is a denser medium, and this is a rarer medium. So light is coming from a rarer to a denser, and the refractive index of the surface is mu. So let a plane wave front, AB is a plane wave front which is striking the surface. First A is striking, it is suffering refraction. Okay, so till the time A comes from A to B dash, B will come from B to A dash. B will come from B to A dash. Okay, now we know refractive index is equal to the speed of light in air to the speed of light in the medium. So let it be C1 and C2. Correct? Now let this angle be the angle of incidence, and this angle be the angle of refraction. This is the angle of refraction. Okay, so here if this is I, this angle is also I. So first of all, please watch here. The time in which A comes to B dash is the same as the time in which B will come to A dash. B will come to A dash, the same time. In that same time, B should come to A dash. The time in which A comes to B dash is the same as the time in which B comes to A dash. Clear? Please note it here. So this is angle I. If this is I, this is also I. If this is R, so here please note here, if this is the angle of refraction, so this is also the angle of refraction. Now we can tell the distance covered by B to A dash is C1t, as you can see here. The distance covered from B to A dash is C1t. So B A dash is actually what? C1t. Okay, similarly the distance covered from A to B dash will be what? C2t. The distance covered from A to B dash, please watch here one thing. Okay, so the distance covered from A to B dash, as you can watch here, this one, A to B dash will be how much? It will be, this is C2 into T, and this one is C1 into T. Correct? That means if I now take sine I will take perpendicular by the hypotenuse. So in the angle of sine I, please watch, what is sine I? Sine I is perpendicular B A dash by A dash. It will be C1t by A dash, C1t by A dash. Similarly, sine R will be AB dash by A dash, C2t by A dash, C2t by A dash. As you can see, sine R is perpendicular, that is C2t by A dash. That means now if I do sine I by sine R, it is C1t by C2t. A dash will cut, T will cut, and that is called refractive index. Sine I by sine R, C1 by C2 is the refractive index. So we are getting sine I by sine R is the refractive index. That means this was the Snell's law of refraction. That means we are able to prove through the wave theory the Snell's law of refraction. We are able to prove the Snell's law of refraction. That means the wave theory can also prove the laws of refraction and the reflection. And moreover, we can also see here that the incident ray, the normal, the refracted rays all lie in the same plane. So this was the second law of refraction. That means laws of refraction was also established by the wave theory. Laws of refraction was also established by the wave theory. Clear? So let us see next what is there. Okay, now frequency. What is frequency? It is the characteristics of source and it remains constant. Please note here, frequency will always remain constant. Okay, as light travels from one medium to another, frequency will never change. Frequency will never change. So frequency is 1 by time period. So mu was velocity of the wave in the first medium to the second medium. Okay, and v, since we know v is equal to f lambda, v equal to f is also called as nu lambda. So v equal to v1 equal to nu 1 lambda 1, nu 2 lambda 2. But we know that frequency never changes, so they will cut. That means mu equal to lambda 1 by lambda 2. That means lambda is inversely proportional to the refractive index, which is very important. That means more the refractive index, less will be the wavelength of the light. Next is superposition principle. What is that? Superposition principle. So according when to the superposition principle, what does it tell? When two or more waves, so see here we have taken two waves. When two or more waves, one is a dotted wave and one is a dark wave. One is a dark line, one is a dotted line. So when two or more waves are traveling through a medium, superimpose one another, a new wave is formed which has a resultant displacement y at any instant, which is equal to the sum of the displacements due to the individual waves y1, y2, y3, etc. That means, so watch here, please let me make you understand. That means if suppose I am drawing it with two different colors so that you can understand. So this is the first wave, having displacement y2, and this is the second wave having displacement, this is the second wave having displacement y2. So at sometimes the waves displacement will add up, giving you a new wave. The wave's displacement will add up, giving you the resultant wave where the displacements are added up, or they will be subtracted. They will be subtracted when y1 and they will be subtracted, giving you a resultant wave. You see, when the two waves are opposite, they will be subtracted. So that is what they are telling. That means when two or more waves are traveling in the same direction, the net displacement is the sum of the displacements of the waves. Okay, so if they are in the opposite direction, they will take the sign of minus, and if they are in the same direction, they will take the sign of the plus. So same direction, the net displacement will add up, and in opposite direction, the net displacement will subtract. Okay, so this is the resultant wave. Let me show you. This will be the resultant wave due to the bow. So here, this is the first wave, this is the first wave, and this is the second wave. So they are in opposite directions. So the resultant of these two waves will be the third wave. Okay, so this is how the waves superimpose, and that is called superposition principle. Now let us study addition of light waves. That means if I take two waves How will I add the waves? So let us take two waves. Let us take the two waves. Oscillating electric field P. So this is a first wave and this is the second wave. So this is the amplitude of the first wave, amplitude of the second wave, okay, frequency of the first wave, frequency of the second wave, phase of the first wave, phase of the second wave, and these waves are produced by oscillating electric field. Mind it, that means there is an oscillating electric field which is producing two waves. Now we know intensity of a wave is directly proportional to the square of the electric field here. So we can write intensity will be this of the first wave. Similarly, intensity of the second wave will be this. Okay, please watch here. There is a term cos square. Please watch here. There is a term cos square. If you take, see, this is very, very important to note this particular thing. That is, if you want to try the average of cos x from 0 to 360 degree, the answer will be 0. And if you want to find the average of cos square x from 0 to 360 degree, the answer will be half. Please note this point. Please note this point, that if you want to find the average of cos x from 0 to 360 degree, cos x will keep varying from 0 to 360 degree. If you want to find the average of cos x from 0 to 360, it is 0. And if you want to find the average of cos square x from 0 to 360, it is half. Clear? Now, taking this in mind, now let us see ahead. Next, what is there? So, average intensity of the first wave will be, because the wave equation was having cos square. Please see, intensity of the first wave, it was having a term cos square. So this whole value will be half. Similarly, this is also having cos square. Its whole value will be half. Its average will be half. That means, now if I take, so average intensity of the first wave will be this. See, half has come. Second wave will be this. Half has come. So the instantaneous intensity at any point will be, we will add these two. Okay, we will be adding these two. K E1 plus E2 square. So this is K E1 square plus K E2 square plus 2K E1 E2. Now this is I1, this is I2, and this is I due to 1 and 2. I due to 1 and 2. I1 we know is this much, I2 we know is this much. Total intensity due to both the waves will be this, K into E1 plus E2 whole square. Now let us find out what is I12. I12 is actually what? 2K E1 E2. So we can write 2K A1 A2 cos omega 1 t plus phi 1 into cos omega 2 t plus phi 2. We are writing the value of E1 and E2. Okay, so 2 goes inside. So this is 2 cos A cos B, and the formula is cos A plus B by 2. This is cos, we are writing 2 cos A cos B. So what is the formula of 2 cos A cos B? It is cos A plus B plus cos A minus B. Okay, cos A plus B plus cos A minus B. So this is our A and this is our B. So here we can write it. Now this is the average of cos theta, which will be from 0 to 2 pi. So this value will become 0. This value will completely become 0. Okay. Similarly, average of this will also become 0. If omega 1 is equal to omega 2, that is also 0. So what are we left with? We are left with k a1 a2 cos phi 1 minus phi 2. We are left with k a1 a2 cos phi 1 minus phi 2. So this part, please watch k a1 a2. What is k a1 a2? So k a1 a2 is actually 2 root I1 I2, because I1 is this, I2 is this. Okay, so I'm showing you I1 is k a1 square by 2, I2 is k a2 square by 2. So therefore a1 a2 should be what? A1 a2 should be what? Root over 2i1k into 2i2k. That means 2k root i1 I2. So this is what we are writing. So k will be k a1 a2 will be k a1 a2 will be root over 2 I1 I2 cos phi 1 minus phi 2. Average of this will be always 0. Average of this part, average of this part will be 0. And in the second part, if omega 1 is equal to omega 2, this is 0, so only this part remains. So this is what we are getting, I12, intensity of one due to the other. So now let us see. That means our equation gets transformed into this. So this is the resultant intensity, I equal to I1 plus I2 plus 2 root I1 I2 cos phi 1 minus phi 2. Phi 1 is the phase of first wave, phi 2 is the phase of the second wave. And please note this, to obtain interference we need two sources with same frequency and with a constant phase difference. So it will be called as a coherent source. Please watch this very carefully. This is a very, very important note. We need two sources with same frequency and constant phase difference. That means this part should not keep on changing. Phase difference should remain constant and frequency of the wave should not change. Okay, and so such two sources will be called as a coherent source. So we need coherent sources for obtaining the interference pattern. Okay, we need coherent sources. So next, when we have two independent, so coherent sources, how can we get? From the single source we get two waves which will be in the same phase and same frequency always. But when we have two independent sources, suppose one is S1 source, one is S2 source, even of the same frequency but their phase difference, that means the phi 1 minus phi 2, this will never remain constant with time. This will never remain constant. So they are incoherent sources. So superposition of such light waves from such sources do not show interference. Please note that superposition of such waves will never show interference of light. Superposition of such waves do not show interference of light if your phase differences are not constant. Clear? Next. So what is a coherent source? So question is coming, what is a coherent source then? What is a coherent source? Very important question. The sources of light which emit continuous light waves of same wavelength, if it is emitted from the same source, they will emit same wavelength, same frequency, and in same phase or having constant phase. They only are called coherent sources. So for interference, I need coherent sources. So as you can see, it is written here that the phase difference between the two sources must remain constant. The phase difference should remain constant. They should be of the same frequency, same wavelength, and the phase difference should remain constant. Next question, which is very, very important topic. Two independent sources cannot be coherent. As I was showing you here, two independent sources, S1 and S2. They can never be coherent. Why? Very important to note. Why they cannot be coherent? That means why cannot they can keep the same frequency and same phase? This is because light emitted from individual atoms when they return to the ground state, so the phase difference do not remain constant, which is required for interference. So for interference, what do we need? Constant phase. We need constant phase difference, which is not possible if you take two different light waves, because they will never be remaining same phase. Okay. Two coherent sources can be obtained from a single source by reflection or refraction. So from a single source, how can you obtain two coherent sources? By reflection or by refraction. Please keep in mind. Next, conditions for obtaining coherent sources. Very, very important. How will you obtain coherent sources to get interference? Number one, coherent sources of light should be obtained from a single source by some device. That means either by reflection or refraction. The two sources should give monochromatic light. Very important. You cannot take white light. The path difference between the light waves from two sources should be small. So these are the three conditions for the interference to happen. That means for coherent sources, you have to obey this. Number one, they should be from a single source. Second, the two sources should use monochromatic light. Okay. Third, the path difference between the two sources should be very, very small. Very small. Next, interference of light. Now we are going to study the very, very important topic, which is interference of light. It's a very important topic. So what is it? It is the phenomena of redistribution of light energy in a medium on account of superposition of light waves from two coherent sources. See, this is a coherent source. This is a single source. It is producing light of two waves. One is going this side, okay, and one is going this side. So they are of the same frequency and maintain same phase. So when these two light waves superimpose at some places on the screen, you will get bright and dark, bright and dark, bright and dark, and the central is always bright. The central will always be bright. So that is what they are telling. That is, in interference of light, there is a redistribution of light energy. So see, redistribution means somewhere it will be bright, somewhere it will be dark, somewhere it will be bright, somewhere it will be dark on the screen. So that is why they are telling redistribution of energy on account of superposition of light waves from two coherent sources. So these are the two coherent sources. A and B are our two coherent sources. So this is a coherent source A, and B, which are giving off lights like this of the same frequency and same phase. So at some points they will be superimposing each other, at some points they will be cancelling out each other. So where they will be superimposing each other, you will have a bright band, and where it will be the two waves will be cancelling out each other, it will be a dark band. So alternate this energy distribution will take place. So see here, at some points where the crest of one falls on the crest of another. So if this is one wave, and if the crest of one falls on the crest of another, if this is the other wave, crest of one falls on the crest of another, like this, that means here the amplitude will become maximum, the intensity will be maximum. And if the crest of one falls on the trough of another, that means if this is one wave, and if the another wave's crest falls on the trough, this is the trough of the first wave. So if the crest of one falls on the trough of the another, like this, that means they will cancel out each other. So resultant amplitude will be minimum, intensity minimum, and the distribution of light, and then you will have a dark band there, and this distribution of light energy is called the interference of light. So you have to have it with a coherent source. Now we will do the double slit experiment. Young's, who was the first to do this experiment, so let us now see what Young's has done to do this experiment. Young's double slit experiment. Young's double slit experiment. So let's see. So first of all, Young is taking a narrow slit, 1 millimeter wide. This is the narrow slit, 1 millimeter width, illuminated by a monochromatic light. A and B are two fine slits of 0.5 millimeter. These are also, this is A 0.5 millimeter wide, B 0.5 millimeter wide. So when a screen is placed at a large distance from A and B, here is the screen, alternate dark and bright fringes appear on the screen. As you can see, dark and bright fringes, these are the interference fringes. Please note. So these dark and bright parts are called the interference fringes. The fringes disappear when A or B is covered. If I cover up A or B, the fringes will not take place, because superposition of two waves will not take place. According to HYGENS principle, the monochromatic light source S sends out spherical wavefronts which reach A. So see, these are the spherical wavefronts which are reaching A and B. Clear? They become source of secondary wavefronts having same amplitude and frequency with zero phase difference. That means from here again new waves come out. So these are called secondary, and which have the zero phase difference between them, So these are the secondary wavelets which come out. Next, when these waves on superposition produce interference, the dots, you see, these are the dots. I can show you. These are the dots. So the dark dots are constructive interference Well, crest, that means the crosses, where you can see the crosses. Here is the cross, here is the cross, here is the cross. So the crosses are the positions of destructive interference. That means you will have a dark band there. The energy and amplitude will be minimum there, and that is what you can see on the screen. That means at some positions you can see that the crest of one is falling on the crest of another bright band, crest of one is falling on the trough of another dark band, crest of one falls on the crest of another bright band, crest of one falls on the trough of another dark band, and this continues. So here amplitude will be maximum intensity maximum, amplitude minimum intensity minimum. The bright and dark fringes are equally spaced. That means the thickness of the bright fringe and the dark fringe will be equal. And please note here one thing, that is, if S is a source of white light, the interferent fringes are colored and unequal widths. Please note, this is very, very important. If you would have, I told you, in the source S you have to use a monochromatic light. Please watch here, we are using a monochromatic light. But if you use a white light, then your fringes will be colored and unequal widths will take place. Okay, next let's see conditions. Very, very important part from where numericals come is this part. Conditions for constructive and destructive interference. So please watch. Let the two coherent sources of light given out will be, one is y1 is a sin omega t, one is y2 is b sin omega t. So see, frequency is same, but there is a constant phase difference of phi. Amplitudes are nearly same. Frequencies are same, but there is a constant phase difference of phi maintained. So these are coherent sources. Okay, so now we will do superposition of these two waves. So what is the resultant displacement? Y equal to, according to superposition, y should be equal to y1 plus y2, y1 plus y2. Okay, so let us open this up. Sin A plus B is sin A cos B plus cos A sin B. Now we will keep both the sin omega t's together and the cos omega t separate. So let us take A plus B cos phi as r cos theta, A plus B cos phi as r cos theta, and then, so as you can see from here, that if I take A plus B cos phi as r cos theta and B sin phi as r sin theta, then please watch here, squaring r square cos square theta will be this, and r square sin square theta will be this. So if I add both, this will give you r square, because cos square theta plus sin square theta is 1, and b square cos square phi plus b square sin square phi will give you b square, and this is 2ab cos phi. So r will be this is the resultant of this. Now this we have taken as r and this we have taken as r. That means we can write this we have taken r cos theta. So this is r cos theta sin omega t, r sin theta cos omega t. Taking r common, we get sin omega t cos theta, cos omega t sin theta, which is actually sin omega t plus theta into r, where r is this. So this is the resultant amplitude of the superposition of the two waves. Okay, and we know intensity square of the amplitude. Intensity will be always square of the amplitude. So please keep in mind that this is the resultant displacement of the superposition of the two waves. Resultant displacement of the superposition of the two waves, and this amplitude of that resultant wave will be this. Amplitude of the resultant wave will be given as this. Very important to note this. This is how you find the amplitude of the resultant wave, R, and this is the displacement of the resultant wave. Displacement of the resultant wave, and we know the intensity square of the amplitude, we know that. So that means the intensity of the first wave is this, the second wave is this, because the amplitude of the first wave is A, amplitude of the second wave is this, and intensity of the resultant wave will be K into R square, which will be this. So if I take this, resultant intensity will be what? Ka square plus Kb square plus 2ab k cos phi. Ka square is I1, this is I2, and this is root I1 I2 cos phi. This is the most important formula of the resultant intensity of the superposition of the two waves. Okay, now we will find out this intensity, where is it maximum, where is it minimum. So for maximum, we know we call it as a constructive interference. For maximum interference, that means for a bright band, if I want to have a bright band, that means that is called a constructive interference for a bright band. So we want to find out what is the condition for a constructive interference. So for constructive intensity should be maximum, that means cos phi should be maximum, and cos phi is maximum when it is plus 1. That means the phi should be either 0, 2 pi, 4 pi, that means n pi. Please note here, when the phase angle, phase difference between the two waves is 2n pi, okay, n is 0, 1, 2, 3 like this, then only the intensity will become maximum. Intensity of the resultant wave will be maximum when the phase difference will be 2n pi. Very important. So if x is the path difference between the two waves at P, so please watch here, what is this I'm talking about? Let me show you. In the diagram, let me first show you here. Suppose one wave reaches like this, another wave reaches like this. So what is the path difference between the two? This is the path difference, this much. This much is the path difference. Clear? So that we have to find out what is the path difference between the two waves. So let's see here. So the path difference, as I have shown you, that the path difference for constructive interference, that means between the two waves, if x is that path difference, then phase difference phi, please note that formula, this is the relation between path difference and phase difference. Very important. This is the relation between path difference and phase difference. Path difference and phase difference. So let me highlight this properly for you. This is the relation between path difference and phase difference. X is the path difference, phi is the phase difference between the two waves. Clear? So this is actually X. Please 1 minute. This is the path difference is lambda by 2 pi into phase difference. So phase difference is 2n pi. That means the path difference is n lambda. Please note these two formulas are very important, and resultant intensities formula is very important. So these three formulas for doing numericals is very, very important. That means phase difference is 2n pi, path difference is n lambda, and this is the resultant intensity for the constructive interference. Okay, so let us now find out for the destructive interference. Let us now find out what is the condition for destructive interference, means where there will be a dark band. For formation of dark bands, what will be the condition? So let's see. Cos phi should be minimum, and cos phi's minimum value is -1. That means it should be a pi or a 3 pi or a 5 pi. That means 2n pi, 2n minus 1 pi, 2n minus 1 pi. This is the condition for phase difference for destructive interference. Now we know path difference is lambda by 2 pi into phase difference. So putting the phase difference, this is the condition for the path difference of destructive interference. So please note that these two formulas are very, very important formulas. Very important formulas. Okay. Now for constructive interference, we know cos phi is 1. So it was a square plus b square plus 2ab cos phi, which is this, and which is this. That means the resultant amplitude will be the sum of the amplitude. Okay, for constructive interference, resultant amplitude will be this, and resultant intensity is square of the amplitude, which should be this, k into a plus b whole square. Clear? This is the resultant intensity for the constructive interference. So destructive interference, the path difference is 2n minus 1 into pi, and the path difference, phase difference will be 2n minus 1 into pi, and the path difference will be 2n minus 1 into lambda by 2. Now we want to find out the next conditions for the destructive part. Okay, so let's see here for destructive interference. So please watch. For destructive interference, of the light, we know cos phi is -1. We know that cos phi is -1. So this will resultant amplitude will become this, which is a minus b. So intensity will become k into a minus b whole square. This is the resultant amplitude. For constructive it was a plus b, for destructive it is a minus b, and for destructive interference the intensity is k into a minus b whole square. That means the relation between interference for constructive and destructive is this. Now if a is equal to b, if the amplitude of the two waves are equal, that means R max, the resultant amplitude will be what? 2a, and R min will be 0, because it is a minus b. R min will be a minus b, so a minus a will be 0. That means the dark band will be very dark and the bright band will be very bright. So I min will be definitely 0, intensity will become very 0. Thus dark fringes will be completely dark. Now this is the relation for the resultant intensity, we know that. Now if omega 1 and omega 2 are the widths of the two slits, please note that, as I told you, that there will be two slits we will be taking. One will be at A and one will be at B. So if the slit widths are omega 1 and omega 2, if the slit widths are omega 1 and omega 2, that means we can write this relation: omega 1 by omega 2 is I1 by I2, which will be A1 square by A2 square. Very, very important, because slit width is proportional to the intensity. Slit width will be proportional to the intensity of the light. Width of the slits is proportional to the intensity of the light and proportional to the square of the amplitudes of the waves. Very, very important topic. Next, interference and energy conservation. Please note that. Now, as you know that in interference pattern we have alternate dark and bright bands. So at the dark band the energy becomes zero, but energy cannot be destroyed. So is the energy conservation violated? So let us see. In the interference pattern, intensity of light is simply being redistributed, that is, energy is being transferred from regions of destructive interference to the region of constructive interference. No energy is being created or destroyed in the process. Thus the principle of energy conservation is followed. That means when we talk about the dark band, in the screen we are seeing this is the bright band and this is the dark band. Again there is a bright band and there is a dark band. Again there is a bright band and there is a dark band. So the question is, in the dark band there is no energy. So is the energy in the dark band destroyed? No. It is being transferred to the bright band. It is being transferred to the bright band. Transferred to the bright band. So no energy is created or destroyed. It is, energy is just being transferred. So energy conservation principle is still obeying here in interference. Next, what will be the fringe width of the interference pattern? Fringe width, that means this width, this width, this width. What is the fringe width? So let us see. A and B are two fine slits separated by a distance d, and a monochromatic light of wavelength is used. So we will always be using a monochromatic light. So we are using a monochromatic light here. Mn is a screen at a distance of d. So this is the screen placed at a distance of d, as you can see here, d. The two waves starting from A and B superimpose, resulting in the interference pattern on the screen. So these are the two waves coming from here, and another wave is coming from here. Okay, so this is the path difference, this is the path difference. So the two waves are meeting here. Either they can meet constructively or they can meet destructively. If they meet constructively, here will be a bright band. If they meet destructively, there will be a dark band. And suppose it is at a distance of x from the center, x from the center. Okay, so let us make the diagram little bit clean. So now what we will do is, okay, C is equal distance from A and B. So watch here, where is C? Here is C. It is equal distance, that means this length and this length are equal. So there is no path difference between the two. Path difference between the two waves will be 0 at C. So C has maximum intensity. That means maxima. So the center will always be a bright maxima. The path difference between the two waves reaching P, what is the path difference? This is the path difference, okay, which will be BP minus AP, PP minus AP. Now what is PE? Please watch here. PE will be PC minus EC, which is X minus D by 2. And what is PF? PF will be PC plus CF, which is X plus D by 2. So now we are taking the triangle BPF. BPF, we are taking the triangle. Okay, so we can write BF square plus PF square to the power half. If I want to find out, okay, BP, if I want to find out BP square will be what? BF square plus PF square root over. Okay, this is actually what we are finding, BP. Clear? So BF square plus PF square. So if I add these two, BF square is what? D. So D square plus this square. So taking the D common out, we can write like this, and using binomial theorem we can use this. This is what? This is, we are finding, this is BP. Similarly, if I want to find AP, so what is AP? AP will be AE square plus PE square root over, which is D square plus X minus D by 2 whole square to the power half. And if I take D common, so we can write like this, using binomial theorem we can use this. So this is the AP. Now path difference is BP minus AP. So BP and AP, if I subtract, then we are getting this. Solving this, we will get this, which is XD by D. So this is the path difference between the two waves which are suffering interference, This is the path difference between the two waves. Very, very important. XD by D. XD by D. Now for bright fringe, we know the path difference has to be n lambda. The path difference should be n lambda. That means XD by D should be n lambda. So X should be n lambda D by D. This, at this distance we will get bright fringes. So if I put n as 0, we will get at the center bright fringe. If I put n equal to 1, we will get at this much distance, we will get a first bright fringe. If I put n equal to 2, we will get at a distance this from the center, we will get the second bright fringe, and this will continue. So the path difference is XD by D, which should be n lambda. XD by D should be n lambda. For a bright fringe, we know that this is the condition for a bright fringe. So this is the path difference should be n lambda. Please keep in mind. Okay, so from there we are getting the position of the different bright fringes. First bright fringe will be n equal to 0. Second bright fringe will be formed at this distance, putting n equal to 1. This is the first bright fringe, second bright fringe, and at the center we will get the bright fringe. Now if we see for a dark fringe, we already got for a bright fringe, that is the minima condition, distance of the bright fringe, a dark fringe. So for a dark fringe, the path difference should be 2n minus 1 lambda by 2, which should be this very important formula. xd by d should be 2n minus 1 lambda by 2. So putting n equal to 1, we get the first position for the first dark fringe, putting n equal to 2, position for the second dark fringe. Now we want to find out what is the fringe width. So if I can find out the distance between the gap between two dark or bright fringes consecutive, that gap will give me the fringe width. So let's see. So that means, suppose fringe width is written as beta. The first bright fringe will be what? As we have seen, the first bright fringe will be d lambda by d, and then it will be 2d lambda by d. So first, the second bright fringe will be at distance 2d lambda by d minus the first bright fringe is this. So the fringe width will be d lambda by d. So this is the fringe width for a bright or hence all fringes are of the equal width. This is very important, please note it. All fringes will be of equal width, because fringe width has got nothing to do with any other. All the variables are constant here. All the variables are constant. So fringe width either for a dark band or a bright band will be same. Next, when we use a source of white light, please watch here, the interference fringes will be colored, but the central fringe will be white. Very important. They ask you what will happen if we use a white light. The interference fringes will be colored and the central fringe will be white, because all the colors will fall on that. Next is, if now wavelength of red light is more than wavelength of violet light, that means if I use monochromatic light of red length, red, so fringe widths will be more. But if I take wavelength, the monochromatic light as violet, the fringe width will be less. So fringe width for for red lights are more than fringe width for violet lights, because it is directly proportional to the wavelength. Next, so friends, next let's see what is there next. Conditions for sustained interference of light. Sustained interference, that if I want to get a interference pattern, if I want to constantly get interference pattern, what are the things I have to maintain? Number one, the two sources of light must be coherent. Very important. That means they should emit continuous light waves of same wavelength or frequency and should have the same phase, constant phase difference between them. That means coherent source is a very important. Second, the amplitudes of the waves from two sources should nearly be equal. Third, the two sources should be monochromatic. And fourth, the coherent sources must be very close to each other. Fifth, the two sources should be point sources or very narrow sources. So see, these are the very important conditions if you want to get a good interference of light. If you want to get a good interference of light, you have to follow these conditions. Next, we will find out what is fringe shift. Fringe shift. So please watch here. Fringe shift. if a transparent, please watch here, these are the two monochromatic sources falling on the screen and we are getting alternate bright and dark bands. Now if I introduce a glass plate of thickness T in any one path, okay, you see, if I introduce here, the bright band will shift upwards. If I introduce here, the bright band will shift downwards. That means there is a shifting of the interference fringes taking place. So if I introduce a transparent sheet of refractive index mu and thickness T in any one path of the interfering waves, the optical path length of this path will be mu t. Optical path will be mu t and not t. So there will be already, it was initially optical path was t and now it has become mu t. So what is the increment? Mu t minus t, so mu minus 1t. This is the optical path's increment. Okay, so the fringes will shift by how much? This. It was x d by d. Fringe, it was lambda d by d. It was actually lambda d by d. So now it is mu minus 1t into d by d. Okay, and the distance will be, now we know that beta equal to lambda d by d. So d by d is beta by lambda. That means the fringes will shift by this much distance towards the ray where the material was introduced, towards the ray where the material will be introduced. The path difference will be this. Okay, so it will be d by d into mu minus 1 t and beta equal to lambda d by d. So as this is independent of n, the entire fringe is shifted. The shifting is towards the path in which transparent plate is introduced. So see, whichever side the transparent plate is introduced, the fringe will shift to that part. By how much? By this much. But fringe will not change. The fringe will not change. It will just shift by this much. The fringes will not change, but it will shift by this much. Okay, so this completes the theory part of the interference by the Huygens principle. Okay, we have completed the theory part, and now what we will be doing is we have to do some numericals based on this. So let's see the numericals. First, if two slits have width ratio, so omega 1 by omega 2 is given to us. We know this relation. Intensity, amplitude. Deduce the ratio of the intensity at maxima and minima in the interference pattern. So fringe, the slit widths given. Okay, so we can easily find out what is A1 by A2 ratio, which is this. And now maxima to minima, we know this condition was there. I max was A1 plus A2 whole square. I min was A1 minus A2. So A1 by A2 I know. So keep putting the values and we get the intensity of maxima to the minima ratio. Again, slit widths of two slits are given. Intensity ratio of the interference pattern they are only asking. That means this is known to us. So we can get the ratio of the amplitude. So I max by I min we can find out. Putting the values of A1 and A2, we can calculate the ratio of the maximum intensity to the minimum intensity. Next, the width of one slit is double the other. That means omega 1 is double of the omega 2. This is given. Means omega 1 or omega 2 is twice of omega 1. This is given to us. So we know this relation. Okay, so from here we can easily see omega 1 by omega 2 is 1 by 2. So that means a1 by a2 will be what? Root over. a1 by a2 will be what? Root over 1. This will be this should be root over. Okay, so it should be what? a1 plus a2 if the amplitude is proportional to the slit width. Okay, so they are telling here, so we don't have to take this. Basically, amplitude is proportional to the slit width. They are already giving the information to us. That means amplitude is proportional to the slit width. So amplitude ratio will be also the slit width ratio. So then I max by I min we can easily find out using this condition. Putting the values we can find out this condition. Next, two coherent sources of intensity. Intensity ratio is I1 by I2 is given I by 4I. Okay, I by 4I. I1 by I2 is given this. And we know intensity and amplitude ratio is this. So we can get the amplitude ratio. If I know the amplitude ratio, I can find out I max by I min. 9:1. Okay, so that is the ratio of the maximum intensity to the minimum intensity. Next, let's see the sum. Is a double slit illuminated by the wavelength. So wavelength given, slit width given. That means this is our D given to us. D is given to us as this slit width, and screen is placed at 1 meter. So capital D is given to us. They are telling what is the angular position of 10th maximum in radian. Angular position of 10th maximum. Okay, so we know that the 10th maximum, the maximum will be formed at this much distance. Okay, this is the center, these are the two waves, this is the D, this is the distance between the two slits, small d. So the 10th maxima, the maxima condition is what? The maxima condition will be what? This is the distance at which the maxima is formed, n equal to d lambda by d. So 10th maxima, and d I know, wavelength I know, d I know, so we can find out this distance. And since they are telling that this angle we have to know, we know sine theta is equal to x by d. Sine theta is very small, so sine theta can be taken as theta, x by d. So this is the x by d, so we are getting this as the radian. Okay, this is the angular position of the 10th maxima. Next, separation of the two adjacent minima. Two adjacent minima means it is the fringe width, d lambda by d. Okay, so putting the values of lambda, d and d, we get the distance between two consecutive minima, which is the fringe width. Next is there is a red light of this much wavelength. Interference is two slits are placed. So d given, wavelength given, distance of the screen is not given, fringe width is given to us. Interference bands are placed 1 centimeter apart. That means fringe width is given to us. So fringe width formula we can use, and we can find out the distance of the screen from here. Next, we want to find out the next sum. Let us see what is it. Okay, so they are telling that the distance between the central bright fringe and fourth dark fringe. Okay, so x dark fringe's distance is given by this formula, where n equal to 4. Okay, and screen distance is 1.5 meter. Slit width is given to us. wavelength I don't know, x is also given to us. X is also given to us. So we have to calculate the wavelength from here. Next, slits are this much distance, that means D is given to us. Screen distance is given to us, and the distance between central bright fringe and fourth bright fringe is 1 centimeter. That means up to the fourth bright fringe. So this is the bright fringe formula. Distance of the bright fringe, x equal to nd by d lambda. So x is known to us. So we have to find out the wavelength from here. Everything is known to us. Putting the values, we calculate the wavelength. Let us see the next sum. The width of the fringes, wavelength is given. Fringe width beta is given to us. Fringe width, this is beta given to us. What will be the fringe width if the entire apparatus is dipped in a liquid of refractive index? This, okay. So see, fringe width is given to us here. Now when the apparatus is dipped in a liquid of density this, now we know that wavelength is inversely proportional to the refractive index. So what will the wavelength then become? This wavelength is inversely proportional to the refractive index. So when the apparatus is dipped in a refractive index of liquid this, so what will the wavelength become? This. So what will be the fringe width then become? This. Okay, putting the value of lambda dash. So we will calculate it. So this is actually coming beta by mu. Beta by mu. So this was the fringe width, mu, refractive index, we get this. Next, the interference fringes are obtained on a screen. So screen distance is given to us. Third dark band is at a distance. Third dark band's distance given to us. Find the wavelength. So dark band's condition, this is the dark band's distance condition. N is 3, distance is given, D is given to us, okay, and slit width given to us, lambda is not given to us. So from here we'll calculate the lambda as this. Next is the wavelength if the entire apparatus is dipped in a, again we know wavelength is inversely proportional to the refractive index. So putting this will be the wavelength of the wave if the apparatus is dipped in a liquid. So now let's see the next sum. The next sum says if the frequency of light used is this is frequency given, distance between the centers of adjacent bright, that means this is beta given. What is the distance between the slits if the screen is, that means they are asking D, and D given, beta given, frequency given. So we know C equal to F lambda. So wavelength we can find. Now we know wavelength, and using this formula we can find out the D. We can find out the D. Two sources are 1.5 millimeter apart. So this is the D given. Fringes are obtained at 2. So this is a D, capital D given. Screen distance, wavelength of light given. If the wavelength is this nanometer, find the number of fringes in the interference pattern, which is 4.9 meter long. Okay, so the distance of the interference, this is okay, so the distance of the interference fringes is this given. Okay, so first we will find out the fringe width, which is this. That means each fringe is of this much width. So in a total distance of this much, how many such fringes will be there? So number of fringes will be that distance by the fringe width. So 5 fringes will be there. So let us calculate the next sum which is there. The angular width of fringe formed on a distant screen is 1 degree. Okay, fringe, the angular width is 1 degree, which is x by d, theta equal to x by d. The wavelength of light used is this. What is the spacing between the slits? Okay, so please watch one thing. Angular width is beta by d. This is the angular width. That means lambda by d. So this is given 1 degree. Angular width is lambda by d coming. Okay, so d equal to lambda by the angular width. The angular width is 1 degree. 1 degree means pi by 180 radians. So using that we get the angular width. Clear? Of each fringe. It is the angular width of each fringe. So please keep in mind. Next, the wavelength of light is given to us. Angular width is given to us. Angular width is what? Angular width, as I told you, it is beta by d. Beta by d. Angular width is beta by d, which is also lambda by d. Angular width is this lambda by d. Okay, so what is the angular width if the, what is the angular fringe separation if the entire apparatus is immersed in water of frequencies? So this wavelength will become how much? Lambda by mu. So lambda by d is this angular width by mu. Okay, so the angular width was given 40 degrees, so this is the radians by 4 by 3. So this will be the angular width if the apparatus is dipped in the water. Next is as you can see from here, the central fringe produced by a light of wavelength lambda given is shifted to the 5th bright fringe by introducing a thin film. So this is the shifting, shifted to the 5th bright fringe. Okay, so we know the path difference will be mu minus 1 into t, which should be the bright fringe. So its path difference should be this. This is the path difference caused by the shifting. Path difference due to the introduction of the film will be mu minus 1 into t. We have done that. And path difference for the bright fringe is n lambda. So equating it, we get the thickness of the film. So next we will find out from here the interference fringes. This is the wavelength given. Angular width is given lambda by d. We know that angular width, please note this formula, lambda by d. Okay, for what wavelength will the width be 10% greater? Now angular width will increase by 10%. If it was del theta 1 before, it is now del theta 2. Del theta 2 is 10% more than this. That means 11 by 10 of 0.2 degree. Clear? So this is lambda 1 by lambda 2. We can find out the lambda 2. Interference fringes with wavelength given, angular width given. What is the angular width if the entire apparatus is dipped in water of this? So we know again angular width is lambda by d. This, so it will be lambda 1 by d by lambda 2 by d. dd will cut. It will be lambda 1 by lambda 2, but lambda 2 will be lambda 1 by mu, which is mu. So del theta 2 will be del theta 1 by mu. So this is the angular width caused. Okay, so let's see the next sum. two waves of intensity ratio given to us. Intensity is square of the amplitudes. So if the intensity I know, then amplitude will be this. Now they are telling, find the ratio of the resultant intensity at a point when the waves are incoherent and the waves are coherent and differ by phase 60 degree. Okay. So please watch one thing. When the waves are incoherent, no interference occurs. That means we will have no interference at all. Okay. So here we will be having the intensity as this much only. That means interference will never occur. Okay, so there is no use to find out the intensity. But when the waves are coherent, interference will occur. So I2 will be this, I1 will be this, I1 will be this. This is I2. So I1 and I2 will be 10:13. Please remember, I1 and I2, when the waves are coherent, then the resultant intensity will be this. And the waves, when the waves are incoherent, then what will happen is that the interference will never occur. So in this case, the resultant intensity, that means there will be no phase at all. No phase, that means there will be, the phase differences will be 90 degree. Okay, phi will be 90 degree to each other. We will not take any phase here. This part will not be there. And when they are coherent, then this formula will be taken. We will find the intensity here, and this is the intensity when it is not coherent. And now we have to compare this. Next is, let us see what will be the phase difference and the path difference between the light waves, third bright fringe and third dark fringe from the central fringe. Okay, for a bright fringe, we know the phase difference and the path difference is this. For a dark fringe, the phase difference and the path difference is this. Okay, so for the third fringe, the phase difference and the path difference for the third fringe will be this, and for the path difference for the third bright fringe and third dark fringe will be this. Which is, this is n lambda. Okay, so this will be the thing. They are telling what will be the path difference and the phase difference between the two. One is a dark fringe, one is a bright fringe. Okay. Next is, among two interfering sources, let A be ahead in phase by 54 degree. 54 relative to B. Okay, 54 degree means the phase is 54 degree, means this is in radians. Phase I know. If PA minus PB is 1.5 lambda, so the path difference is given to us. We know path difference is 2 pi by lambda into phase difference. This is the phase difference is 2 pi by lambda into phase difference is 2 pi by lambda into path difference. So we find out this. So total path difference will be 0.3 pi plus 3 pi, which is 3.3 pi. Okay. Find the phase difference between the waves reaching from A and B. Okay. So that means the phase difference between A is ahead in phase by 54. Already there is a 54 degree phase ahead. That 54 degree means this much ahead. and when it is going, it is still making a phase difference of 3 pi. So in total, how much phase difference? This plus this. It was the original phase difference, and now while traveling it is making this much phase difference. So now total phase difference will be this. Okay, so let's see the next sum. So here they are telling, calculate the difference between the fourth bright fringe and third bright fringe. So bright fringe distance is this. Fourth bright fringe, put n equal to 4. This. Third bright fringe, n equal to 3. This. Now find the on other side of the central bright fringe. That means if this is the central bright fringe, here is a fourth bright fringe and here is the third bright fringe. So what is the distance between them? So find the distance of this, find the distance of this, add them. So this is what we added and we get the answer. If the interference pattern of 10th bright fringe and wavelength given is observed at a point, what order maxima will be visible if lambda is this? Okay, so 10th bright fringe distance, so n equal to 10, we get that distance. Okay, so this is the wavelength. Okay, fine. So question they are telling that interference pattern for 10th bright fringe is observed. So for 10th bright fringe, this is the calculation, and if I do it with wavelength 5000 angstrom, this should be the calculation. So I don't know n, that means they are telling they are equal. So from there find out the n. So 14th bright fringe will be formed if you do it with a wavelength of 5000 angstrom. If the screen is moved this much meter towards the slits, the change in the fringe width is this. If the distance between the slits is this, that means d is given to us, and screen is moved this much, find the wavelength of the light used. Fine. So here initial fringe width was this. Okay, and now the screen has been moved by this much, so now the distance of the screen is only this much. So this should be the fringe width. So by how much has the fringe width changed? This, which is this. So they are telling the fringe width change is given as this. So from there we can calculate the wavelength. Next we can use a beam of light which has wavelengths. See, there are two wavelengths given, this and this. What is the least distance from the central maxima where the bright fringes due to both coincide? Okay, d given. So bright, what is the least distance from the central maxima? Okay, so for this wavelength, let the distance from the central maxima be this. For this, let the t given to both. Okay, first wait. What is the least distance from the central maxima where the bright fringes due to both wavelengths coincide? Okay, the distance would be same. The distances would be same. Okay, so this distance and this distance, what is the least distance from the central maxima? Okay, so first let the nth bright fringe coincide with the n plus 1th bright fringe, but the distance from the center would be the same. So x is same. So from here we can calculate the value of n. That means 4th bright fringe due to this wave and 4th bright fringe due to this wave will have the same distance from the center. Okay, Find the minimum thickness of a film which will strongly reflect the light of this. The refractive index is this. So for strong reflection, the least optical path introduced by the film should be lambda by 2. Please watch this point, you have to note. For a strong reflection, the least optical path difference by the film should be a multiple of lambda by 2. This. That means 2 mu t should be lambda by 2. From there we can find out the thickness of the wave. 2 mu t. Okay. For strong reflection, the optical path difference should be this. So we know that it was mu minus 1 into t, okay, plus mu plus 1 into t, which will give you 2 mu t. This will be the optical. For that means when the light is falling, minus when plus when the light is reflecting. So light falls here and light reflects here. So this is the total path difference, which should be equal to lambda by 2. Next is a transparent paper of refractive index this, thickness this, pasted on one slit. The light used is this. How many fringes will cross through the center if the paper is removed? Okay, so see, we know due to the introduction of the slit, the slit's interference pattern will shift by this much, beta by lambda mu minus 1 into t. Okay, it will shift by this. So number of fringes which will fall under that distance will be this, which is this. So putting the values, we calculate it. That means it will shift by this much distance up or down. And if each fringe width is beta, so how many such fringes will fall in that distance? The formula is this. The fringe pattern shifts by a certain distance when a mica sheet of 1.6 and thickness this. So this is the t, this is the mu given, is introduced in the path of the wave. The mica sheet is then removed, and we know that on introduction of the mica sheet, the fringe will shift by this much, which is this much. And now they are telling the mica sheet is now removed and the distance between the screen and the slits is doubled. It is found that the distance between the successive maxima now is the same as observed fringe shift upon the introduction of the mica sheet. Find the wavelength. Okay, so now they are telling that the screen distance is now made twice. So what is the fringe width? This, which is twice of this. Okay, and they are telling that the please watch here one thing, 1 minute. Okay, if the sheet is removed and the distance between the screen and the slits is doubled, okay, so it becomes 2d. So the fringe width will be now twice of the fringe width. It is found that the distance between the successive maxima now is same as observed fringe shift. Okay, fringe shift. Okay, the distance between the successive maxima is the same as the fringe width. That means this will be now 2 beta. So beta and beta will cut. From there we can find the wavelength. So friend, this was the total discussion of the interference due to the Huygens principle. We have studied the optics interference due to the Huygens principle. Hope you have understood, but I would request you, please go through the theory very nicely before you start with the numericals. So my first request is that please go through the theory 2-3 times at least. Make your own notes, make your own formula, and then only you can try with the other things, not before that. Okay, so if you have understood it, please make a comment, give a comment, also leave a comment, and if you have any problem, please then also please leave a comment. And my request is, please keep watching Parijat sir classes. Do subscribe it for getting more and more updates of the new videos, so that you can be thorough with the syllabus. Okay, because I am discussing each and every chapter in details. So till then, it's goodbye from my side, and hope you have understood the lecture clearly. And my request is, please keep following the things, and please make note of the things. That is the only thing in which you can make the things simpler. Okay, thank you so much.